streaming this now. I just started streaming. You can probably log on to it now. Hi Vivek. Hi Monica. Good morning. Hi Riddhi. Hello. Today I could connect it. But anyway, that's good. Good morning everybody. I am just starting now. So let us start considering the systems of differential equations. You might wonder, we have been working on a seemingly simple equation, namely y derivative equal to f of xy. It's a first order equation in one unknown. It's an ordinary differential equation, and you have seen the difficulties in solving this equation when the function is not something simple enough. That is, f is not simple enough. Even this problem may pose a lot of questions, and in fact we have sorted out most of it, namely the general questions like whether a solution exists for an initial value problem or not, and so on. So natural question that comes to one's mind is this. Often you come across higher dimensional or higher order differential equations. how does this serve such equations? Obviously it doesn't. Okay. So we have to work out a machinery which is capable of handling the higher dimensional equations. If you recall, I started in the beginning with a dynamical problem of the motion of a particle in a force field. In that we had three simultaneous second order equations, each for the what is called the x component, y component and z component of the position vector. So something like this, d2x by dt square equal to f of x y z t, d2y by dt square equal to f2 of x y z t, and then f3 x y z. So the three unknowns constitute what is called the position vector. So r is given by x y z, that is xi plus yj plus zk if you were to use the conventional notation. And then we converted this into a system of differential equations, system of first order equations, by introducing some ad hoc or additional variables like the velocity. So essentially we introduce three more variables: v1 equal to dx1 by dt, dx by dt, or I will put it u equal to dx by dt, v equal to dy by dt, w equal to dz by dt. These are the velocities in the x direction, y direction and z direction. So if you know you said you dynamically you know the particle, if you know what position it occupies and with what velocity it is moving. Therefore you found that this system of equations govern the motion of a particle. And then we said that we can convert this into a first order system in 6 unknowns. The 6 unknowns are x, y, z, that is the first 3 coordinates correspond to the position. The next 3 components are v, u, v, w, which corresponds to what is called the velocity components. So this is something that we have seen, and eventually the equation takes the form something like this. It's a vector. T is the independent variable. Now x has components. Sorry, x, y, z, u, v, w. And f has components f1, f2, f3, f4, f5, f6. 6 components are there. And you see that this consists of the following. The system, actually if you write it down, this is what happens. dx by dt equal to u, dy by dt equal to v, dz by dt equal to w. Then what you have is, I am sorry, even this may carry even this dx by dt, dy by dt, dz by dt, and t. Yeah, and the same thing here, same thing here. So what you have, this one, then you have See, you can write this d2x by dt square can be written as du by dt. So du by dt equal to f1, dv by dt equal to f2, dw by dt equal to f3. So you see that it's a system of 6 first order equations. That transformation can always be done. In general, we will later write down the format. You can transform any higher order equation into a equivalent first order system. Therefore, if we develop the theory for a first order system, then you are done. The general theory is done for a first order system. And that gives that helps us to work out the problem. So let me see where we start. So let us start writing down a first order system. So let us take x1, xn as the dependent variable, t as the independent variable, and let f1, f2, fn are n functions of each fy is a function of xn and for I equal to now it's just a matter of introducing the right notation, then everything is done. So we will write x as the dependent variable as xn and capital F, which is a function of x and t, as now we can write down a set of first order equations given by dx1 by dt equal to f1, dx2 by dt equal to f2, therefore it's immediately clear that with these notations, now if x1, x2, etc. xn are functions of t, then x is a function of t. So what you have is this dx by dt t is the independent variable. This is how the system looks like in a very compact notation, which you compare with the following: dy by dx. I think I have by habit you write it as fxy, but actually fyx in this language. So I put a semicolon there to separate the dependent variables and the independent variables. So the problem is there are n dependent variables, one independent variable, therefore it's an ordinary differential equation. So this is what you call a system of n first order differential equations. So it immediately suggests to you that maybe whatever we did for this equation can be mimicked for this also, and you can develop a theory. Okay, so our objective of these lectures would be to give an exposition to how we proceed in this case. And you can almost, I mean, you can see that almost all the theorems that we have developed there has the analogous representation here. And the small things that you have to do are just, get the right kind of notation. And then once you are through that process, the theory automatically is suggested and developed. So that's the point. A second point I wanted to emphasize is this is demanding in the sense that, you see, how to work in a general metric. So, see, it's a one-dimensional space. You are working with a part of R. Okay. For instance, you see, you look at this one. This is a part of R2, where X is the independent variable which varies over R. Y also varies over R as a function of X. This is as X varies, Y varies with that. And what you want to know, it is interlocked with the derivative of Y. Therefore, what you are asking is, what is the solution of this particular equation? And maybe some initial data also. So, we will come to that initial data later. Okay. So, how do you reframe the whole thing? I mean, that is the thing. And when you reframe it, again, there are problems. If you look at F, see, X belongs to R. Over an interval contained in R, it may be the whole of R. Okay. Now you see that if you look at these equations, this set of equations, you see that you cannot solve just one of the, except in some examples, specific examples, because the derivative of x1 is also related to the change that takes place on x1, x2, etc., xn and t. Similarly for all these, so they are all interlinked, and therefore you cannot solve one equation, each one of them separately and then put together. So this is the problem. So that's why you call it a system. It's a system of n first order equations in n unknowns with t as the independent variable. Now if you look at this one, what is f? F is a map from some region omega of, I'll put it this way, say D cross the interval I. This is corresponding to the variable. You see, I am writing this as x. So x belongs to D. D is contained in Rn, and I is, T belongs to interval I. So this is the setup that you have. So you are working, so F is a map from D cross I to R, to R. It's a real valued function, so it's a vector valued function, so it's to R. Okay, with n components. And if you look at each of these Fi, Fi is a map from now we can make some assumptions about D, I and R. Okay, so D is it may be the whole of Rn. And t of course is, as I said, yeah, please. Yes. Any? Hello? Yeah, parayu. Tell me. Exactly, yes. It's a part of Rn plus 1. Yeah. Is it okay? Yeah, it's not f is not a real valued function, it is an Rn valued function with n components. Yeah, because you have f1, f2, etc. fn, you are writing fxt as f1xt, f2xt, etc. fnxt. Is that all right? Okay, so what you have is this fxt So that is the structure of this. Now this clearly tells you something, that we are working, so this omega is considered as a part of Rn. Now we want to separate the independent variable and the dependent variable. So we will introduce the following. We will write x, this is the notation, x as x1, x2, xn, and we write norm of x as the Euclidean norm, this is the Euclidean norm that you have. You can introduce any norm, in fact, because whatever norm is convenient for your computation, you can make use of, because if all these topological results are valid in one norm, then it is valid in any other norm, because all the norms are equivalent on these finite dimensional cases. But in general, we use the usual standard norm, which in R2 it will look like this. If you have 2 points x1 and x2, then this is 0 and this is x, then norm of x is the direct distance from 0 to x. That is given. The usual, you know all these things. Now xt is for t belonging to some I. Now you can imagine in the n-dimensional space, a point is given by x1, x2, etc. xn. Now as t varies, this point starts changing position. Okay, so it moves. So you can imagine this as the movement or the motion of a particle along a path. So it traces essentially, as time moves over the interval I, the particle traces a path in the n-dimensional space. Okay, right? Let us go back to our original example, where you have the 6-dimensional phase space. That is what I called it. The first 3 components talks about the position, the next 3 component talks about the velocity, and therefore you see that in the 6-dimensional space, a point corresponds to the position vector and the velocity vector. Okay, so that is the sort of situation that you encounter here. Now we say that, see, x is a map from I to Rn. Now we say that x is continuous at t naught belonging to y. Is the usual definition. What is the usual definition? The usual definition is, given an epsilon neighborhood of see, you have x t naught, there exists a delta neighborhood of t naught, so that every point in the delta neighborhood of t naught gets mapped into the epsilon neighborhood. Okay, so for any positive epsilon, this is true, that the given epsilon there is a corresponding delta. So this is the usual definition, and one can prove that this is equivalent to the statement that every component function, which is a real valued function, is continuous. So we will just make that observation, and I think it needs a proof which you can give. So that's the sort of result that we prove. We say that x is continuous if and only if each component xi is a continuous real valued function of t. So this you try to prove. When you say x is continuous, x is taken as a map from I to Rn, and you say that this is, you see, you have a topology here, you have a topology here. Okay, you have the usual metric here, and here you have a metric. Therefore both are topological spaces. You can talk about mappings from one topological space into another topological spaces, and then you have the standard definition of continuity, and that's what we take. So what we are saying is, in that sense, x is a continuous function of t if and only if each component function xi is continuous real valued function of t. So try to give a proof. So I leave it to you to prove this. It's a good exercise. They are very elementary but important. Now we say that xt is differentiable if and only if each xi is differentiable. Now you can actually work out the derivative. Okay, it's quite easy to, because what you do is you are working, there is no complication about this. X t naught plus say h minus x t naught divided by h, limit. Now this in the sense of norm, etc., etc. So I mean there is no complication because h is a real number, so division is no problem. Now this is equal to, see, you have got each these are the n components of that. Therefore, you can adopt the notation that x derivative of t is what you write. Now, of course, f of xt is I have described this. These are all, each one of these component is a real valued function. So f is a map from omega to r. You can have the notion of continuity. You have a topology here, you have a topology here. So you can talk about continuity of f with respect to the variables. So these are all usual things. Now our differential equation is then of the form which tells that dx1 by dt, dxi by dt equal to fi x, which is equal to fi of this is the differential equation that we look at. Now what about the initial conditions? So let me write down the initial data. The initial condition is, what was the initial condition in the one-dimensional case? You had a point in D, that was the space. So here what we have is this, x naught t is a point taken in omega. Okay, x naught t naught, sorry. That means x naught belongs to D and t naught belongs to I. This is what you have. Okay. Now if this point is given, then you have D, the initial data will be given by x at t naught, x at t naught equal to x naught. Just compare with y x naught equal to y naught. So t x naught y naught is a point point in D. There D is of course the first variable, there is the independent variable, second variable is the dependent variable. I have put it in the other way around in this notation. Okay, does not matter at all. So once you properly recognize it, it is fine. Okay, so the one-dimensional version of this, compare with that. This is the initial value problem that we look at. Now we can write x naught, I write as that's a fixed point belonging to D. Okay. So we shall assume that capital F of is a continuous map continuous function from what is that? This is omega into omega is D cross I. Now we can define a region in this part. So it is something like this. You see, you have as we have done earlier, you have the point x naught, t naught, and then now what we are going to do is we are going to form a rectangular box. Okay, so let me denote by R the set of all points xt such that mod or norm of x minus x naught is less than or equal to B, norm of t minus t naught, which is the modulus of that, is less than or equal to A. Okay. We had x minus x naught less than or equal to A, y minus y naught less than or equal to B. So same thing, except that we have replaced now mod by the norm, the appropriate norm. So you can see the evolution of the generalization going from our experience in one dimension to moving into higher dimensions, and how the notations, how the new terminologies, everything has come up. Okay, so from R to Rn, then the next stage is going to a topological space. I mean that is not required here. So we are working all the time in metric spaces. So this R is now a part of omega. That's what we have, such that R is a part of omega. Now we have assumed that capital F is a continuous function on omega. Function, the vector valued function on omega, which in turn implies that F, because R is now a compact space, a compact subset of Rn plus 1, okay, because it is omega is in, see, D is in Rn, and the other variable I is a part of R, therefore it's a part of, so this is a part of Rn cross R, which you can take as Rn plus 1, and you can talk about the norm of that. So you have this one, this implies F is a continuous, okay, what is that I wanted to say, is bounded on R. Because this is the reason, okay, it's this compactness essentially, it's closed and bounded, therefore you see that F is a bounded function on that. Let norm of F, I put it as modulus, but you will have to read it as the norm. What is this? This is actually this is it, okay, and you see that this is less than or equal to some F, or in other words, you have this box, I mean on this box F is a bounded function. Now we define an approximate solution of the initial value problem. See, I'll give a simple example after making this statement. Okay, let us look at an example to get a feeling for this. Okay, so if you take the case where, okay, let us look at this dynamical problem. Where V equal to W and F is equal to F1, F2, F3. So what you get is in R3, see, this gives a force field. For example, in the flow of a river, now you see that when the river is flowing, at each point there is a velocity vector. Okay, so what is that you have in the river? You see that it's considered as a three-dimensional thing. Then what you have is that at each point you have a vector. Okay, the components of this vector are F1, F2, f3 where fi is a function of x, y, z and t. This may also depend on t. What does it mean? It means that the velocity field that you had at a point at a time t1 is not the same as the velocity vector that you have at the point x1, x2 or xyz at the time t2. It may differ, will change. I mean, as you see in the flow of a river, then this happens. I mean, may not remain the same. But you may have situations like where there is a sort of steady flow in which it does not vary with t at all. That's also possible. Okay? And then we are looking at the flow, the motion of a particle. Suppose you drop a leaf here, so at some point, at some time t equal to t naught, what you are looking for, what is the path of this particular leaf as time evolves? This is the question that you are asking. Okay, so that's the initial value problem. So I think I gave an idea of the dynamic idea of this, but that's a good image that's worth carrying, and many problems will finally boil down to this particular language. Now we are going to talk about what is called the approximate solution. Okay. So we have this problem. This is the initial value problem. What do you mean by an approximate solution? An approximate solution of the differential equation system dx by dt equal to f of xt with an error epsilon positive maybe even 0. When epsilon is equal to 0, it becomes an exact solution. Okay. Is a continuous admissible function x of t for t belonging to some interval with piecewise continuous derivatives such that what is it? X derivative of t minus f of is less than or equal to x. That's an approximate See, now what do you mean by admissible function? See, over the interval I, okay, we say that xt is an admissible function if this happens, that is, what is it? Xt should belong to the what we call the omega, then only f is defined. So what we need is the function should have the property that when it is defined for each value of t of the interval I, xt is such that f of xt t should be defined, and that can happen only if the argument of f, namely xt belongs to omega. That is a primary condition, so that f makes meaningful. Because if something is defined, is not defined in some part of, they say for example, suppose this is D, okay, and if you take a point outside this, and suppose f is defined only here, suppose you take a point outside here, obviously small f is not defined there, okay. So what we want is an admissible function, means that for whatever value of t that you take, xt t has to be in the domain of f. That is the condition that you have, so that this becomes meaningful. And what you need is that you are looking for a piecewise continuous function, which means it's a continuous function, but piecewise, with a piecewise continuous derivative, means that there are intervals on which it is differentiable, but not necessarily everywhere it is differentiable. I mean, that means it is differentiable except for a finite number of values of t, and the derivative is it is piecewise continuous, the derivative is piecewise continuous. So you have a partition of the interval such that on each of the sub intervals the function is a differentiable function. Fine. And then what you have is that you can evaluate f of xt. What is this is a vector in Rn, and x prime t is also a vector in Rn. So the difference between these two should be in the sense of the norm of Rn should be less than epsilon. So that is the criteria. So the meaning of this modulus that I have put here is that it's a norm in R. So once you get the notation clear, then everything is fine. And the same statement for the initial value problem is that in addition to this, that xt should satisfy the condition xt naught equal to x naught. So t naught should belong to the interval I that you have, and there at t naught xt naught should be equal to x naught. Then it's an approximate solution of this initial value problem with error epsilon. So that's the usual idea that we have pursued earlier. Now what I want to, I'll just do the analogous theorem of the existence of this. So what you have is this. Okay. So let me given epsilon positive, there can be constructed an approximate solution of the initial value problem of the differential equation T with error epsilon over the interval mod t minus t naught less than or equal to h for some h, where h is taken as minimum of a b by, where m is the bound for f in R. So we started with a rectangular box region, and there this is the solution. I mean, this is exactly analogous to the statement that we have made earlier. Okay. So how do we proceed with this? We proceed exactly as we did in the previous case. What was the procedure? See, you had the interval t0 to, and of course on this part also. Let us look at the side t0 to t0 plus h. What we say is that there is a partition t1, t2, tn minus 1, this is tn, okay, of the interval. How do you proceed from here? From f t0, see, from t0, what we do is, now you see you are in this particular region, okay, this is your d. At t0 you are here, at x0. Now what do? You have a vector there, this is a vector in Rn. So you move along that vector over the time interval t0 to t1 and then find out where you reach. Okay, this is corresponding to t1. Then what you do is, you know the coordinates of this point is some x1 t1 or x1 at t1. So what do? You calculate f of x1 t1, okay, and then you will move in this direction. So it's exactly the same thing that we did. Okay, so you start with the point x0 t0, you have f of x0 t0, move along the direction of f of t0 x0 until up to the time t equal to t1. Then find out where you reached. You would have reached a point x1 t1. Compute f. There is an f there because you consider it as a velocity field. Okay, and then proceed in that direction until you reach the time t2 and so on. You can go on in this way, so you get a sort of broken thing like this. Now let us write down that. Therefore, you see that, so let me write down the outline of the proof. So so we begin with the point x naught in D at time t naught. Now you have the vector field f x naught t naught. You proceed further along the direction until t equal to t1. Then find the position x1 we have arrived at. Now what you do at x1 t1, find f t1. f x1 t1 is a vector again in Rn. So you proceed until you reach and then continue. This is the procedure. Okay, so what do you get? So we have to substantiate. So this is the process that you indulge in, and then what you get? One gets the approximate solution will be xt equal to xi minus 1 plus t minus ti minus 1 f of xi minus 1. This is what you get. Okay. Now this is for the interval ti minus 1 less than or equal to t less than or equal to ti. I equal to. So what you have obtained is a partition of the interval t naught less than t1 less than t2 etc. tn, which is equal to t naught plus h. This is the partition that there you have obtained this as the description of this. Now what do? We will do the following. We have to get this epsilon. So how you connect this epsilon with the time interval, the partition of the interval. So that's the main process. So we want to that the time interval gets shorter if you are asking for greater accuracy. Okay, so let us fix this. How do we fix that? Note that it's a continuous function. Therefore, what we have, given epsilon positive, there exists a delta positive such that we are just using continuity for R, the rectangle box R, mod norm of x1 minus x2 is less than or equal to delta so corresponding to an epsilon positive you have a delta such that whenever x1 x2 x1 t1 and x2 t2 are such that norm of x1 minus x2 is less than delta, norm of t1 minus t2 less than or equal to delta, what one gets, okay, this such a delta exists. Now choose the partition of x t0 to t0 plus h as h such that mod or ti minus ti minus 1 is less than delta. Sorry, less than minimum of delta okay. Now you can estimate. Then the approximate solution that we have defined, the approximate solution has the property what is the property? Property that dx by dt f of is less than epsilon for mod mod belonging to all t belonging to except at t1 now of course you can write except at the tn. Okay, So you see, this is what you can do. So you have to estimate this using this function. Okay, and then you try to prove that take dx by dt. When you take dx by dt, what you get is on this interval it is going to be f of xi minus 1 ti minus 1. So you are taking the difference between f of xi minus 1 ti minus 1 and f of xt. Okay, so then you make use of this continuity restriction that you have, or the choice of epsilon and delta to prove this result. Okay, so I will stop here, right? I will continue with this in the, so that gives the outline of the proof, exactly as we did in the one-dimensional case. What you do is, see, in all these n-dimensional cases, one nice way to learn this is take n equal to 2 or 3, where you can almost see what is going on and do the computations. Then it will be clear, and after that you push it across to n. Okay, thank you very much. So I think I will return by 12 o'clock, right? So is there any questions? Okay, fine. So we will meet at 12 o'clock.